Today we're going to go another step farther in studying the complications to our ideal circuits. Last year, all our circuits were ideal, meaning we had perfect batteries, perfect wires, and perfect light bulbs. We've already learned that batteries can deviate from the ideal when we try to draw a lot of current from them. So two AA batteries are supposed to give us 3 volts, but when we try to get more current out of the battery, we see that the voltage begins to drop. This drop takes place in a linear fashion, so as we get more current out, we get less voltage measured on the terminals of the battery. We saw that when batteries age, their slope increases, and the greater the slope, the worse the battery is. We saw that if a battery had 0 slope, like the purple one, it would act like our ideal, which we studied last year. Most times, in fact all times, batteries will not have a slope of 0, but if we're measuring small currents, milliamps, microamps, we can assume that there's not going to be any change in voltage to the battery. Okay, so today we'd like to look at season 2 of Stranger Things. Instead of looking at the Stranger Things of batteries, let's look at the Stranger Things for light bulbs and wires. So we did a lab the other day where we had an ideal light bulb and a real light bulb, and we measured voltage and current for different circumstances. So we changed the voltage and we measured how much current was flowing through the different light bulbs. We saw that there was a deviation between the real and the ideal, and I'd like to talk about why. So if you take a look at this light bulb, right now the filament inside is at room temperature. When I start to put more voltage across the terminals of this, okay, you could see in real life and up here, you could see that this thing starts to get hotter. More voltage gives you more current gives you a higher temperature, and here's the key. The higher temperature means that this thing is going to have more resistance. Higher temperatures in this filament create higher resistances. So the resistance of that bulb does not remain constant. And this is going to be true for all types of wires. When the temperature of the wire changes, the resistance of the wire changes. Okay, so again, we ran our experiment and we got 2 different graphs. The red one is ideal circumstances, like we would have thought of last year. This is a perfect Ohm's Law relationship, where when we double the voltage, we double the current. The problem is, in real life, that's not how it's going to look. In real life, as we just saw, higher voltages gives you higher currents, and higher currents, if they're high enough, can cause the material to heat up, and the higher temperature creates a greater resistance. A greater resistance is going to give you a smaller slope, so you can see how the slope of this thing gets less and less as time goes on. A higher resistance gives you less slope because that means you're going to be able to get less current for a given change in voltage. Okay, so again, ideal follows Ohm's law. The blue one is called non-ohmic, meaning it does not follow Ohm's law. The slope changes because the resistance changes. This graph shows you just how complicated this change in resistance is for real materials. There is no way for scientists to know ahead of time exactly how a given material will behave. So they experimentally create graphs that look like this. So they would test different materials like copper and platinum and nickel and iron, and they would test their resistance at different temperatures and plot it out. It turns out that for many of them, like iron, the relationship is quite complicated. For copper, you could see it's kind of a straight line, and for platinum, it's very much a linear relationship. For nickel, it looks like it's linear, but it changes slope at a certain point. So the bottom line is, it's a complicated relationship between temperature and resistance. Every material behaves differently. Some materials change how they behave over certain thresholds of temperature. So the only way to know is to actually experiment ahead of time so that engineers in the future don't have to repeat the experiment. They could draw off of this graph and figure out what's going to happen in a given circumstance. I'd like to focus on this non-common material. It's actually an alloy containing manganese and copper, and it was developed to have almost a slope of 0, which means that it does not change resistance significantly with temperature. It's got a pretty high resistance to start with, so it's good to use in resistors. And it's also nice if those temperatures are going to get high because it's not going to change resistance over a very wide range of temperatures. Okay, scientists went one step farther and they developed these little things. They're called thermistors. They are little electronic components that we can put into different circuits. And the material inside the thermistor has been studied so that we understand precisely the connection between temperature and resistance for that material. And then what we do is we put it in a circuit like this, a simple series circuit. We know that the 9 volts will be shared between these two resistors. We know it's not shared equally. So based on how much voltage we get here, we can figure out the resistance of that thermistor. And then based on the resistance, we can figure out what the temperature is. So this little guy right here is like a little thermometer. It's like an electric thermometer. Based on resistance, it can tell temperature. So it can be used to tell us the temperature or to control stuff. So that when certain temperatures are reached, something happens. A refrigerator turns on or an air conditioner shuts off. There's lots of different ways that scientists have figured out how to use these thermistors. Okay, let me show you how to mathematically find resistance for materials where the change in resistance is kind of linear. Scientists developed this nice handy-dandy formula to get an approximate resistance at different temperatures. So here's how it's going to work out. You find the resistance at a reference temperature, usually room temperature. You do that using the formula from last year. Okay, once you know the resistance at room temperature, you plug that into here. You plug in the material, so in this case we're happen to be using tungsten. And you plug in the temperature coefficient. It goes by the letter alpha. You put the temperature it's actually being used at, and tungsten is the type of material you'd find in many of these light bulbs. So the temperatures are really high for those wires. That would get plugged in here. Then you plug in the reference temperature, and for us, all of our resistances are measured in at 25 degrees. 25 degrees Celsius. Okay, so see if you can do this. Take tungsten, plug in the length of 3 meters, plug in the diameter, turn that into a radius, turn that into an area, make sure you're working in meters, use the resistivity of tungsten from your reference sheet, and find the resistance at room temperature. And then see if you can find it at 2700 degrees Celsius. Okay, you don't have to do this one, but for copper, at small temperatures, you're going to find that there's almost no difference between our reference resistance and our new resistance. This is because, as we saw, copper has very little change in resistance as the temperature changes, especially as we do modest temperatures, from like 0 Celsius up to about 200 Celsius. So raising it from 25 to 30 is going to make almost no difference. Okay, so again, bottom line, resistance is not as simple as we learned last year. Resistance changes with temperature. Every material is different. And the only way to figure out how a material is going to respond to temperature changes is to experiment. Record the data and then allow engineers in the future to use your data.